So here's a function, and we're being asked lots of different questions about the function. We're being asked about whether it's increasing or decreasing. We're being asked about whether or not it has vertical asymptotes. We're being asked about some other characteristics of a function having a value of radical 3/2 or not. Anyways, we have this long list of questions, and it seems like the best way to go about answering those questions is to start by graphing this function. Now, when we graph things without a calculator, which is what we're doing here, there's often a strategy that we go through looking for x-intercepts and y-intercepts and end behavior and so forth, but sometimes it's a little bit better just to plot a few points and see if you can get a sense for how the function behaves. In other words, what is happening to y values for various x values. And I'm going to employ that strategy here. So what I'm going to do is I'm going to plot this function, which we're being told is plotted from 0 to infinity. And I'm going to just pick a few integers here to plug in for x. Not that there's anything special about these integers, but if I can find out what's happening to the function for these, I may see a pattern and be able to draw larger generalizations about the function itself. So what I did is I plugged in 0, 1, 2, and 3 for the function. I got when I plugged in 0, I got the cosine of 1. When I plugged in 1, I got the cosine of 1/2, and so on. You may want to pause here and analyze where I got these numbers from. It's basic, but you have to see it before we move on. Now, I kind of cheated in a way and used a calculator to figure out decimal approximations for these. And you don't need to do that, by the way, but I wanted to just share them with you to sort of make a point here. What you'll notice is that starting with x equals 0, the function value is about 1/2. And then as x increases, the function value seems to increase as well. And you'll notice that the answers towards the bottom of the table are pretty close to 1. Now you might say, well, Mr. Rosillo, how would I have known any of this if I'm graphing this without a calculator? What sense does it make to use a calculator? Well, what I'd like to prove to you now is that I didn't actually need a calculator to know that the value of this function would start out at about 1/2, and then as x increased, get closer and closer to 1. Let me share something with you. So let's start at the top. What is the cosine of 1? That literally means the cosine of 1 radian. Well, here's a diagram, and you can see a 1 radian arc starting at the standard point and going counterclockwise. How would we know that that's 1 radian? Well, 1 radian, remember, literally has a length of 1. And if the radius of this circle is 1, you can convince yourself that this curve has a length of about 1. Well, notice the black dot on the x-axis. That is the x-coordinate of the terminal point. Hence, that is the cosine of 1 radian. And you can see by the location of the black dot that it's about 1/2. And that's good enough to know for approximation purposes. Now let's go to the next point. Let's go from 1 radian to 1/2 a radian. I'm going to reduce the arc size to 1/2 that amount, or 1/2 of a radian. And you can see that the black dot on the x-axis, which represents the cosine, got bigger. As the arc got smaller, the cosine got bigger. Now notice, I'm going to now go to the next point, which is 1/3 of a radian. That arc is about 1/3 of a radian, and the black dot underneath the terminal point is the cosine of 1/3. And I think it's easy to convince ourselves that that's pretty close to 1. And if we go to the cosine of 1/4, that's even closer to 1. Let me show you this one more time. Watch what happens as the arc length gets smaller. Watch what happens to the cosine, or the x-coordinate of the black dot. Smaller arc, bigger cosine. And If we were to extend this table even further, you would see that, for example, if I were to plug in 100, I'm sort of analyzing the right end behavior here in some sense, aren't I? If I were to plug in something close to 100, then the argument of the cosine would be pretty close to 0, and the cosine of something pretty close to 0 is pretty close to 1. After all, the cosine of 0 itself is actually 1. So this argument should convince you that the graph of this function starts out at about a half, or whatever the true value of a cosine of 1 is. And then as x continues to grow, the function gets closer and closer to 1 itself. And so you see, just by plotting a few points and having a sense of what the cosine function does, we now have a good sense for what this graph of f of x does. And now that we have a good approximation for the graph of f of x, we can now answer the questions that were asked of us in the first place. Let's start at the top. F is increasing on the entire domain, meaning the domain from 0 to infinity, which was given in the problem. That definitely appears to be true. And it certainly seems reasonable here, based on our graph, that the function is not decreasing on the whole domain, nor is it increasing on parts and decreasing on other parts. Now let's get to the question of vertical asymptotes. For vertical asymptotes, there don't appear to be any, so that would be a true statement. And the two statements underneath it, that vertical asymptotes exist, don't seem to be true. Now for the next statement, there is a positive number m such that f of m equals radical 3 over 2. That's equivalent to saying that this function has a point whose y-coordinate is radical 3 over 2. Watch the y-axis. Radical 3 over 2 is a little bit under 1. You may recall that it's about 0.86 just from memory. And if you look at that mark on the y-axis and you extend over, then there is a point on this graph whose y-coordinate is radical 3 over 2. And the m being referred to in this problem is right here. Now, I don't know what m is, but I'm not asked to find it. The statement we're analyzing above simply says there is such a number, m. I would agree with that statement and mark that one true, even though I don't know specifically what m is. And finally, if there is such an m, then the next statement underneath that can't be true, that there is no such m, so that one is false. And that completes this very challenging problem.